Hey guys, Miss Lowry here. I thought I'd make a series of videos for you guys on all the different topics for optics. Obviously I'm going to go kind of quick through it because you can pause it whenever you guys need to take a second to get caught up on the notes. And if you have any questions, ask Miss Leneve, or you can Edmodo me and I'll be more than happy to help you. So this first video is going to be about revisiting Snell's law and talking about total internal reflection and critical angle. And as we talked about before, the midterm, okay, Snell's law, remember, is the law of refraction, which is N1 sine theta 1 equals N2 sine theta 2, okay? And in the activity you guys did before the midterm, you had a pin that you placed, and you were looking at looking through it through the plexiglass, and you should have seen that when the light traveled through, okay, you should have seen that it bent toward the normal, okay, just like that. So this would be our angle of incidence in the air, okay, and this would be our angle of refraction down here, okay. Zoom in a little bit for you. There we go. So let me make it a little less blurry. There we go. All right, sorry about the shaky table. I don't have a stable lab table. I'm using my dining room table, which is a little shaky, so sorry about that. So we've got our angle of incidence, which is our angle of incidence in the air. This is our angle of incidence, our angle of refraction through the plexiglass. And you should have seen that as this exits, okay, the angle at which it comes into the plexiglass, call that theta I, because that's our angle of incidence, okay. We'll call this theta R, that's our angle of refraction through the plexiglass, okay. We'll call this theta incidence prime, okay, and then we'll call this theta refraction prime. You should see that this angle of incidence here equals this angle of refraction down here, because you're going from air into plexi back into air, so those angles are going to be the same, okay. So you should have seen that your angle, your index of refraction in air times sine of your incidence angle is equal to index of refraction in the plexiglass times sine of your refracted angle, okay? And so if we rearrange this equation, okay, we see that sine theta of our incidence angle, sine of our incidence angle over sine of our refracted angle is equal to the plexi index of refraction over the air index of refraction. Well, if we know that that's equal to 1, okay, then we can see that your index of refraction is basically equal to this ratio, okay, sine theta, your incidence angle over your refracted angle. And that's how you were able to determine what the index of refraction was in the plexiglass, okay. Also remember that we can also find our index of refraction because it's simply a ratio of the speed of light, which is 3 times 10 to the 8th meters per second, over the speed in whatever medium. So speed of light in the medium. So let that be air or water or whatever. Okay. All right, let's move on to total internal reflection and the critical angle. And what that means. Okay, so the critical angle is the smallest angle of incidence for which light is totally reflected. Okay, this angle is reached when the angle of refraction equals 90 degrees. Okay. All right. So let's see. So think of it like this. When you've got two mediums, you've got air, and let's say you've got water, and we have a normal. You remember the line perpendicular to the surface. Okay. We know that as a ray comes in, it's going to bend away from the normal. Okay, because it's going from more dense to less dense medium. So we'll call that like ray number 1. So this is ray number 1, corresponding ray. Okay, but look what happens when, so this is our angle of incidence. It's our angle of, oops, wrong way, angle of refraction. Okay, look what happens when we increase that angle of incidence. So if we increase it to here, we might have, so this would be the second ray. And then there's a point at which, when that incidence ray comes in, it's going to be refracted such that the refracted angle is 90 degrees. At that point, any angle after that, so let's call this ray 3, any angle after that is going to be reflected back into the original medium. Okay, so that critical angle is the angle at which that you get reflection. Okay, the angle at which your refracted angle is 90 degrees and you get total internal reflection. Okay, total internal reflection. So if we look at our incidence, basically, so in this case it would be water, okay, times our sine of our incidence angle is equal to our refracted angle, index of refraction times the sine of our refracted angle. Okay, then we get, if this becomes 90 degrees, sine of 90 is equal to 1. Okay, so what you end up with is this refracted ray, when that's equal to 90 degrees, that becomes your critical angle. Okay, so this component here becomes 1. And so basically the sine of your critical angle, whatever angle that might be, it's going to vary from medium to medium. Okay, that's going to be equal to the index of refraction for, in the refracted medium, the medium it goes into, in this example it would be air, divided by the incidence index of refraction. So this is kind of our equation for critical angle. Okay, so total internal reflection occurs when the angle of incidence exceeds the critical angle. Okay, and you'll get that, we did that before, where you would get sine of, say, you'd try to do sine of some number and it would come up with, you know, domain error. Domain error tells you can't take sine of anything that's greater than 1. So that tells you that you've exceeded the critical angle. And you're going to get total internal reflection, okay, back into your object, into your medium. Okay? All right, our next lesson will be all about lenses and how refraction applies to lenses.